super like multiple times shuttered our laser, and then like they'll shutter it for like 30 minutes, and then you're like, well, that's like enough time to maybe go acquire another target.
Yeah.
And then by that time, we were doing all M31, like it was Clouded clusters in
okay.
M31.
Okay.
And so it's like really frustrating.
That's, yeah. With Gemini though, I've heard about people having problems with Gemini South. Like, I don't think the staff is as good there, and so like getting things observed the way you want it to be observed. And so I've heard of, you know, people who have to like babysit and basically log in and make sure like the right things are being done.
Yeah. They're starting to allow you to do that. They didn't used to allow you to do that even. You didn't know.
Yeah, right. You just got data.
I mean, even with my data, you know, I feel like Gemini NIFS and the laser guide star stuff, it's like the best instrument for that kind of work. You know?
Yeah,
You know,
yeah.
It beats Symphony, it beats Osiris. It's a better instrument.
Yeah.
But even with that, there's just like the boutique offset sky exposures often because of, you know, it's not a very big field of view, so you can't really just do sky selection. So you take the offset sky exposures, and then they will sometimes just like have some problems where they'll miss an exposure or something like that, and they'll just take an offset sky exposure and you'll offset that like a half hour from any of your other exposures.
Oh, yeah.
Sky
Yeah.
So like of the set of data I got this fall, like all but only one of the sky exposures was actually next to the science exposure that it was supposed to be next to, and so the sky spectrum was horrible. And that's really like frustrating.
Yeah.
You know, you can kind of deal with it if you have to, but it just takes a lot of work.
Right.
If they just observe it the way I asked them
Then
to
it
do
wouldn't,
then it wouldn't
yeah.
take all that extra work.
Yeah, that's frustrating.
I'm sure there were reasons, but you know, they don't tell you why.
No, it's all just, you just pound the keyboard when you're reducing the data. No, I had Gemini South was observing for me during the earthquake in 2010. And so the log file was hilarious. It's like, observing, everything is shaking. This seems like an earthquake. Is everything okay? Seems like everything okay. Continue exposure. You know, they just like kept going like, okay.
This is the big Concepcion one, or the one like there was a giant one down south, or the one that?
The big Concepcion one. Wasn't that 2010 or so?
Yeah,
that was the one.
But it was far away from.
Okay, but I guess they felt it enough to make a note, you know, but it didn't mess up anything, but it was still.
Oh, that was a huge base.
Yeah.
Did you? I guess you haven't been down to Magellan and stuff.
No, because I was never in a Magellan institution, so I've actually never been to Chile.
Yeah.
But I'm going for this conference in
Awesome.
March, so.
You should block out. I guess you can't because you're going to be teaching in spring.
I know, it's in the middle of teaching, that's the thing.
Are you teaching the Galaxies course again?
No, I'm teaching majors, like Astrophysics 2 for majors.
Okay. Cool.
So I'm trying to knock out, you're supposed to teach, you know, non-major undergrad, major undergrad, and then grad students, so I'm trying to knock them out and then repeat, hopefully.
Yeah, that's kind of what I do.
Because I'm tired of
top 3 classes.
Yeah. It's the
It gets so
same.
much better when it's
I cannot wait for repeat.
Like I'm teaching tonight from
You are?
7 to 9, yeah. That's why I'm not going out to dinner with you.
What? Your class meets at night?
Yeah.
Is it observing session?
Class. Yeah.
That's cool. Okay. So you get to use your green laser pointer.
Yeah, and early in the semester we do all our observing on the roof.
Okay.
And they do bi observing, and then they do like some CCD observing.
Okay, these are majors?
It's a weird class. It's a mix of major and non-majors.
That's a lot for non-majors to do CCDs and stuff.
Yeah, I mean it's basically we just do, you know, they do take biases and darks and flats, but it's all black box and reduction.
Oh.
It's like they use Max and DL. I don't know.
Okay.
It's like this Windows program that amateur astronomers use.
Okay.
So it's kind of like amateur level stuff mostly.
Hey Pearl, how are you? Good. Yeah, man. I haven't seen you since the time you came back to Austin. So you've been here 3 years, 4 years, 4 years. Okay. So you guys started at the same time. Okay.
Batchmates, as they would say. In India, they call that batchmates.
Batchmates? You're made with the same batch of cookie dough or something.
Yes.
Did you have a 3-year review?
Yeah.
Okay, so but everything is Got through that.
We're good.
We're good. All right, final stretch.
All right. Or should we give them?
So you got this gorgeous Victorian house close to campus, right?
Yes.
Yeah, you're still there?
Yeah.
Good.
Yep. Super happy. And Nav is coming to visit, actually.
Oh,
Tomorrow.
okay. Wow. All your Texas people are coming back to visit you.
I haven't seen Nav since well, no, that's not true. I saw him in Texas. He now lives in the U.S. again.
Okay. Yeah, he was going to South Africa.
South Africa for 4 years.
Wow.
Yeah. And he's now he's moved back to South Africa, back to San Francisco.
San Francisco. Okay. Wow. That's exciting. You'll get to see him a lot more often now. He's in the same continent. Are you teaching this semester? GR. Grad student GR? Okay. Not teaching this semester. It's my research semester, but it's almost over.
She delayed
So
it though from her first. She taught her first semester.
Smart.
that's what I thought I would.
I know. I was like,
Yeah.
I'm not gonna get anything done my first semester anyway, so might as well teach. Yeah.
I'm gonna.
All right. Thank you, everybody, for coming. We're really excited to have Julie Comerford here to tell us about dual black holes and black holes in general. She's an expert in this area. She's been working, she did her undergraduate at Princeton, graduate degree at Berkeley, and then was a postdoctoral fellow at in Texas. And then is now a faculty member at the University of Colorado in her second year, and is happily not teaching, so she's on the, was able to accept our invitation to come and speak with us. And yeah, I will turn it over to her. Just one thing, if anyone wants to come to dinner, Jung is organizing dinner, and the graduate students, she'll be giving a HEAP seminar tomorrow as well. So if you like what you hear here, you can double down tomorrow at 11 a.m. over in ISCC. Okay.
All right. Thanks, Anil. Thanks. Yeah, there's one more week left in the semester at Colorado, so I have one more week to kind of gloat about not teaching this semester, and I have to go back in January. So it's nice to be able to travel now. I don't have to miss classes. So I'll be talking about supermassive black holes and how they can be used as observational tracers of the evolution of galaxies. And in this talk, I'll be highlighting a lot of work that's done by my group at Colorado. So Becky Nevin is a second-year graduate student. She's working on optical long-slit spectroscopy. Scott Barrows is a postdoc working on X-ray data from the Chandra X-ray Observatory. And Francisco Mueller-Sanchez is working on radio data and near-infrared IFU data. So we're a very multi-wavelength group, which is good because I'm going to be talking about active galactic nuclei, which are a very multi-wavelength species of astrophysical objects. But first, to set the stage, let's talk about supermassive black holes. So all or nearly all massive galaxies have at their center a supermassive black hole with a mass of 1 million to 1 billion times the mass of the sun. So at the center of the Milky Way, there's a 4 million solar mass black hole, and we know this because we can track the orbits of the stars, individual stars, at the galactic center, and infer that there must be something physically small but very massive to create these sorts of orbits, and that's how we're able to place constraints on what the mass of the black hole is at the center of our galaxy. Now, if there is a reservoir of gas near a supermassive black hole, that gas can accrete onto the black hole and cause it to light up very brightly as an active galactic nucleus, an AGN, or a quasar. You probably hear both terms. AGN is just the generic term. It can be something faint, or it can be something very bright like a quasar. And quasars can be so bright that they can outshine the entire host galaxy that they're in. So this accretion of gas can be brighter than all of the stars in a galaxy. And so AGN are a good way of looking for supermassive black holes in more distant galaxies where we can't follow the stellar or gas kinematics. And about 5% of supermassive black holes are very bright as these AGN. So, in the context of galaxies, the evolution of galaxies is tied in large part to mergers of galaxies with each other. So here's a simplistic schematic of how this sort of merger-driven galaxy evolution happens. So we start with a single isolated galaxy with a supermassive black hole at the center. We merge it with another galaxy, and this merger induces tidal torques on the gas in the galaxies. It drives the gas towards the center of the merging galaxies. So some of that gas can accrete onto the black hole, cause it to shine as an AGN. Some of the gas also forms new stars. So we enter this very active phase during the merger where there's lots of new stars being formed. There's lots of black hole gas accreting onto the black hole, causing it to shine brightly as an AGN. But eventually feedback from the stars and from the AGN will blow out all the remaining gas and dust from the center of the galaxy. So without any more gas and dust available, you can't accrete onto the black hole anymore. You can't form any new stars. So eventually this merger-remnant galaxy gets starved. It stops forming stars. It just sort of fades and runs away. The AGN turns off. And eventually you get this more relaxed elliptical galaxy at the end. So this picture of merger-driven galaxy evolution leads to several open questions. So we saw that a merger between two galaxies can trigger gas inflows to light up an AGN, but you can also light up AGN outside of galaxy mergers. You can accrete gas onto AGN, for example, along a bar in a galaxy, so you don't need a merger at all. So we want to understand in what cases is an AGN ignited by a galaxy merger and in what cases is it not. We also saw that all this gas accretion onto the black hole during the merger can cause the black hole to grow in mass a lot. And so we want to understand how much gas accretion actually happens onto black holes during mergers. And finally, the merger between two galaxies also leads to the merger of the two supermassive black holes. And this is interesting because when the black holes are about to merge, they emit gravitational waves. So it's a powerful source of gravitational waves. And so in order for gravitational wave experiments to understand what sort of signals they should get from merging black holes, we need to know how often black holes are merging and what the inspiral time scale is. So in the course of this talk, I'm going to introduce this class of objects called dual supermassive black holes as a new observational angle we can take at answering these sorts of questions in galaxy evolution. So the dual supermassive black holes are pairs of black holes in galaxy mergers with separations less than 10 kiloparsecs. So just for reference, the sun is located 8 kiloparsecs away from the center of the Milky Way. So you can think of these black hole pairs as orbiting sort of inside of the solar radius in the galaxy. That's the kind of physical scales that we're talking about. Okay. So let's look at this picture of a galaxy merger again, but this time from the context of what's happening with the supermassive black holes. So we start out with the black holes in isolated galaxies with large separations, so tens or 100 kiloparsec separation. And we can watch as the galaxies come closer together in their encounter. They start the merging, and eventually the black holes are brought close enough together that they're in the same merger-remnant galaxy. And so this is the dual phase. So the separations between the black holes are a few kiloparsec, and they're moving around in the galaxy at velocities of a few hundred kilometers a second relative to each other. They're just following the potential of the host galaxy. Now, dynamical friction from the surrounding stars in the galaxy continue to drag the black holes as they orbit. So they orbit ever closer together because they lose energy from dynamical friction. So eventually they form a gravitationally bound binary system. And here the separations are much smaller, so less than a parsec. So going from a kiloparsec down to less than a parsec. And because they're so close together, the velocities are much faster, a few thousand kilometers a second now instead of a few hundred. And eventually these binaries will coalesce and form a new black hole at the center of the galaxy. And this is the gravitational radiation phase. So I want to focus on this binary step for a moment here, because these are the smallest separation black holes sort of right before the merger takes place. And if these black holes are accreting gas, and if they're visible as AGN, then an AGN has two regions to it. It has a very small broadline region component that's very close to the black hole, and then it has a larger narrowline component that's more physically extended. And so at these smallest separations, the narrowline regions are overlapping, but the broadline regions are still bound to each individual black hole, and so the broadline regions are orbiting with the black holes. And so you can use this as a signature to try and look for these binary black holes. And so this is what people have done. So the binary black holes, you can look for they would have emission lines from each of the broadline regions. And so if the binaries are orbiting around each other, you could see a relative redshift of one of them in one of the emission components and a relative blue shift of the other. And so the velocity separation between these peaks could be 1,000 or a couple thousand kilometers a second. So this could be an observational signature you could expect from binary supermassive black holes, and people have gone out and done searches for this type of thing. But it turns out you can also get this sort of profile from a single black hole where you're seeing the rotation of the accretion disk around it. So you're seeing the relative redshift and blue shift of the accretion disk as it's going around a single black hole. And so a lot of these candidates for binaries have turned out just to be single black holes. So really what you need to confirm a binary black hole system is spatial resolution of each black hole individually, so you can be sure that there's two things there. And this is difficult because remember these separations are very small, less than a parsec in galaxies far away, right? So observationally this is very challenging to be able to spatially resolve these two binary black holes. So far there's been no confirmations of a binary black hole system. So there's been candidates, but no confirmations of binaries. So in my work, what I do is go one step further out in separation to the ones we actually can spatially resolve and confirm. So I work on this dual phase where the separations are of order kiloparsecs instead of parsecs. And the important physical distinction between these two is that the binaries are gravitationally bound to each other, whereas the duals are still far enough apart that they're orbiting in the potential of the galaxy and they're not yet gravitationally bound. Okay. So we can find these dual supermassive black holes if both of them are accreting gas as AGN. And so we call these dual AGN. Now you can do numerical simulations of galaxy mergers where you can follow along the gas during the merger and when it accretes onto the black holes as they orbit closer together. And when people do this, they find that this dual AGN phase does happen quite frequently during the merger of two galaxies. So that's what this plot is showing. This is the velocity separation between the two black holes in a merger, so a few hundred kilometers a second, plotted against their separation. So this would be the very early stages of the merger, and this is as the black holes are getting closer and closer to merging. And the color bar shows the amount of time that the two black holes spend active as dual AGN. So you can see from the simulations that the dual AGN phase, which is less than, when we're at separations less than 10 kiloparsecs, so about here down, that the black holes can spend millions, hundreds of millions of years at a time, or millions of years, few million years active as a time as dual AGN. So according to the simulations, there should be lots of dual AGN at these separations that are produced by galaxy mergers. But the surprising thing is that very few of these have actually been observed. So this was the state of the art 5 years ago. There were exactly 4 known dual AGN. And these were all found serendipitously. People were looking at galaxies for other purposes, and then they found that they had 2 AGN in the core. So the most famous example of a dual AGN is NGC 6240, which is this very messy, ultraluminous infrared galaxy that's in the middle of a merger. And this is an X-ray image from the Chandra X-ray telescope showing the central region of this galaxy. And the 2 blue points correspond to 2 X-ray sources that are coming from 2 separate AGN. And the separation here is about a kiloparsec between these 2. So the way that you can find these AGN pairs is you spatially resolve them either in the X-rays, like in NGC 6240, or in this galaxy down here with separations 4 kiloparsecs, or in the radio wavelengths. So that's what we're seeing here between these two and then these two. And this galaxy is special because this is the smallest separation AGN pair that has been found so far. So this is only 7 parsec separation. So this is getting closer to the binary regime. Okay. So we have all these great things we could do with dual AGN to learn about galaxy evolution, but there's not a lot you can do with a sample of 4. So what we'd like to do is build up a large sample of these things so we can come back and address these open questions in the field of galaxy evolution. So I mentioned that there are 2 different ways you can fuel AGN, through galaxy mergers or through stochastic accretion outside of mergers. And the theory has suggested that there's AGN luminosity dependence here, that the most luminous AGN are the ones produced in mergers, whereas less luminous AGNs are the ones that are stochastically accreting gas. And that's what this figure is showing. So this is from simulations of galaxies that are merging. This is basically a luminosity function of the AGN. And so you can see in red, the merger-induced AGN tend to go out to higher luminosity. So the higher luminosity AGN tend to be merger-induced, whereas the stochastically induced AGN are preferentially at lower luminosities. So this is a very clear prediction from the theory, but the observational results have been conflicting. Some of them say that this is true, the more luminous AGN are the ones that mergers, and some observations say that there's no luminosity dependence at all. So why is there discrepancy? The reason is because observationally, it is difficult to find AGN in mergers. You need to find AGN in mergers to measure this part, right? And the problem is that observationally, it's difficult to identify galaxy mergers in a precise, accurate way. So usually it's done by looking at the galaxy morphologies, their shapes, what they look like, their light profiles. So here's an example of a galaxy merger. You can tell because it looks very disturbed. It's got this tidal tail of stars and gases thrown off during the merger. It's got asymmetries. So this galaxy you would classify as a merger. But the problem is that not all galaxies are as obvious as this one. So you can imagine if you just had some faint tidal features that maybe you didn't pick up in your image, or some asymmetries that are maybe washed out because of projection effects, it makes it difficult to build a clean sample of galaxy mergers to do this work observationally. So, but dual AGN, by definition, they are AGN in mergers. How else are you going to get 2 AGN in one galaxy? So they offer a new, cleaner way of getting at this question of whether there's a luminosity dependence on AGN fueling mechanisms. Now, there's an observed relation between the mass of a supermassive black hole and the velocity dispersion of the stars in a galaxy's bulge. This is called the M-sigma relation. And in order to explain the tightness of this relation, the black holes have to build up some of their mass through gas during mergers. Now, Anil finds galaxies that don't lie on this relation that are way up here and off. But in order to explain the rest, there's got to be some black hole mass growth that's happening during mergers. And so since dual AGN, they are actively accreting gas and growing in mass in the midst of mergers, they're a good sample to use to get at this sort of question too. And finally, the dual AGN are the smallest separation black hole pairs we've been able to find so far, so they can offer the tightest observational constraints on the black hole merger rate, which is important for gravitational wave experiments such as pulsar timing rays to know, so they can know how often to expect supermassive black holes to merge and what sort of gravitational wave signature that should give them. Okay. So we'd like to build a large catalog of these dual AGNs so we can start to answer these sorts of questions. So we want to move past these anecdotal examples of individual systems and onto a systematic search to build up a large catalog. So I'll describe how we do this in 3 easy steps. So the first step is to select good candidates for dual AGN from Galaxy Spectra. So to orient you, here's a spectrum of what a typical single AGN that's not in a merger might look like. So this is the flux versus the wavelength of the galaxy, and this is in the rest frame of the galaxy. And you can tell this galaxy has an AGN because it has these characteristic emission lines. So these are the oxygen 3 lines at 5007 and 4959 angstroms. And there's also H beta, and there's a high line flux ratio of the oxygen 3 to H beta. Now, these dashed lines show the expected wavelengths of these emission lines if they were at the exact same velocity as the stars in the host galaxy. So this is the type of spectrum you get for an AGN that's just sitting at rest at the bottom of its host galaxy's potential well. It's going at the same velocity as the stars. It's not, doesn't have some independent velocity that's due to a merger. So this is not what we want if we want to find AGN in mergers, though. Instead, we'll look for something like this. So instead of having those single peak lines, here we have double peak lines. And so the idea is this could be produced by 2 AGN that are moving in a merging galaxy system. One has a relative redshift producing this peak, and one has a relative blue shift. So this is analogous to the technique that was used for the binary black holes, except with the binaries they were looking at double-peaked broad lines produced by the broadline region very close into the black holes, whereas here we're looking at double-peaked narrow lines, which are produced by the larger narrow line region. But we still have some of those same issues that the double-peaked broad lines did, which are that dual AGN aren't the only things that can produce this double-peaked structure. So that's why there's more than one step to this process of finding dual AGN. Okay, but we'll start with these double-peaked emission lines as a way to select candidates. And the first place we did this was in a survey of galaxy spectra called DEEP-2. So this was a survey of about 50,000 galaxies out at about redshift 1. And so we found 2 double-peaked AGN. You can see the double peaks here and here. And so that was about 2% of the sample of AGN that we had in this survey. Now, the great thing about DEEP-2 is that all of this data was taken with the DEIMOS spectrograph at the Keck telescopes in Hawaii. And so DEIMOS is a long slit. It uses long-slit spectra, which means that we have spatial information as well as spectral, 1D spectral information. So I'll show you what I mean by that. So here's an example of a 2D spectrum that you can get from these long-slit observations. So it's 2D because instead of just having the wavelength axis, we also have the spatial axis along the slit. So this band in the middle, this is the stellar continuum from the host galaxy. And then this is showing emission in oxygen 3 from a single AGN. And so since we have this spatial axis, you can see that this is where the galaxy is centered, and it's the same place as where the AGN is centered. So this is an example of a single AGN, not in a merger. Now I'll show you what the 2D spectra look like for the 2 double-peaked AGN. So instead of a single emission component here, now we have 2. And they're separated in velocity or wavelength in this axis. But then you can also see they're separated spatially along the slit. This one's higher up in the slit than this one. So you can actually measure the spatial separation between the 2 objects, the 2 emission components on the plane of the sky. So that's about 1 kiloparsec for this one and 2 kiloparsecs for that one. So you can see why these 2D spectra are valuable. From the 1D spectrum, we could get the velocity separations, and then now we can also see the spatial separations. So we start to get a better picture of what's going on. Now, the DEEP-2 survey was great for this because it has these 2D spectra that come with, but the downside of DEEP-2 is it's a relatively small spectroscopic survey of galaxies. And so if these double peak things only occur in 2% of AGN, then we really need a much larger sample of galaxy spectra if we want to find large numbers of these double-peaked AGN. So the place to do that is the Sloan Digital Sky Survey. Sloan is big enough that even though only 1 or 2% of AGN have these double-peaked profile, you can find hundreds of them in Sloan because you have spectra for over 1 million galaxies. And so there are 3 separate papers that published double-peaked AGN spectra that they found in Sloan. And these are also galaxies at much lower redshifts than the DEEP-2 sample. So the great thing about Sloan is its sheer size, the number of spectra we have to work with. But the drawback is that it doesn't have those 2D spectra we had for deep. Sloan uses a fiber-fed spectrograph, so we don't have any spatial information. So that leads me to the second step, which is to take all these double-peaked AGN we're finding in Sloan, these 340 objects, and to get some follow-up long-slit spectra to make these 2D spectra for them and learn something about the spatial profiles of the emission and whether they might be dual AGN. So the reason we need to do this is that double-peaked profiles can be produced not just by dual AGN, but also by a rotating disk or by an AGN outflow, outflows of gas from an AGN. So I'll show you an example of the outflow. So this is a nearby galaxy. This is the map of its oxygen-3 emission. It has a central AGN, and all of this extended oxygen-3 emission is coming from a biconical outflow coming out from the AGN. So some of the emission is blue shifted and some of the emission is red shifted. The net effect is you get this double-peaked spectral profile, which looks a lot like the ones I've been showing you, except this is not produced by two AGN in a merger. This is just one AGN with an outflow. And so here's the model of this outflow. So the AGN would be here, and this is the biconical structure of the outflow. Some of it blue shifted, some of it red shifted. And this is their 2D spectrum of what this outflow looks like. So this is the wavelength or velocity axis, and then this is the spatial position again along the slit. So it's got this very extended 2D structure to the spectrum, which they modeled with this outflow. So you can see where the 2D spectra start to come in handy. The 1D spectrum can look the same for dual AGN or an outflow or a rotating disk, but the 2D spectra can actually look quite different. So what we did is we went to several different telescopes over the last few years to get long-slit spectra for these double-peaked AGN in Sloan. And we've used many different telescopes, but right now we're using Apache Point Observatory in New Mexico because Colorado has a share of this telescope. And this is what my graduate student, Becky Nevin, is working on, is getting the long-slit spectra at APO. And so the purpose is to use this spatial information about where the emission is coming from in the galaxy as an extra step to help identify which of these things could be dual AGN. So this is the approach. Here's your galaxy. Here's the spectrum that we already have from Sloan. You can see the double peaks in H beta and in oxygen-3. Now, we don't know, if there are two AGN in this galaxy, we don't know exactly how they're oriented. And so we don't know how to place the slit. And so what we do is we observe at two orthogonal slit position angles so we can be sure we'll get both AGN wherever they are. So we line up the first slit at a certain position angle. That gives us a spectrum. So here's our 2D spectrum from this orientation. So you can see the two emission components separated in velocity corresponding to these double peaks you see in the 1D spectrum. But then also you can measure the spatial separation along the slit. So we'll call that X1. Now let's observe again at an orthogonal position angle. We'll get another spectrum. Still see the two components, but this time the spatial separation is much smaller, almost nothing. So what we've done is we've observed at two different position angles. We've gotten a measure of the separation between emission components at each position angle. And so with a little trigonometry, you can turn this into the actual full separation and orientation of the sky of the two emission components. Okay. So I'll show you what some of these things look like. Here's some examples. So you see at the bottom plot shows the double peak profile from Sloan, and then here are the two slit position angles with the 2D spectra. So you can see some of them have very compact emission components, and then some of them are spatially extended in a variety of different ways. So you can see how this could start to help us sort out which ones look like they could be outflows and which ones could still be good candidates for dual AGN. And since we were able to measure the spatial separation and orientation on the sky of all these emission components, we can plot that up. This is a histogram of the spatial separations we measured between the O3 emission components. And most of the separations are around a kiloparsec. So that means that whatever is producing these double-peaked line profiles is something that's happening on kiloparsec scales. Okay, so that's some progress. At least we know what scales we should be operating at. Now, some of the objects, we found two emission components that actually line up with the location of two stellar components in the galaxy that you can see in high-resolution near-infrared images of the galaxy. So here's one example. This is one of the galaxies that has this double-peaked profile. And when you look at the galaxy stars and the near-infrared image, you see there are two stellar components. And there's emission associated with each one, AGN emission. And so the picture here is that these could be the two remnant stellar cores of the merging galaxies. Each has a central black hole that's accreting gas as an AGN. That's why we see emission associated with each. So these are the really good candidates for dual AGN. And we found 10 or so that look like this. But in order to really know that you have a galaxy with two AGN in it, you need to spatially resolve the two AGN either in radio or in X-ray. And so that's the final step of this technique. So in the radio, the hope is to resolve two radio cores, like in this Galaxy 0402, the record setter for the smallest separation black hole pair. And there have been, so the instrument we use for this is called the Very Large Array. It's a radio telescope array in New Mexico. It's the one from the movie Contact where Jodie Foster's going like this. It's that one. And so it's great because it's a huge array, so you can get really good spatial resolution. You can find things with very small separations. And so there have been two of these double-peaked AGN observed with the VLA. One of them turned out to be dual AGN, and the other one turned out to be an outflow. So those are papers here. And we've gotten VLA observations for another 71 of the double-peaked AGN. In the X-ray, the hope is to see something like NGC 6240, where in the X-ray we saw these two hard X-ray sources corresponding to two AGN. And so this is data taken with the Chandra X-ray Space Telescope. And so 4 of the double-peaked AGN have already been observed with Chandra. 2 of them turned out to be dual AGN, and 2 of them weren't detected in the X-rays for reasons I'll get into. And we've gotten Chandra and Hubble Space Telescope data for another 10 of the double-peaked AGN. So I'll show you what some of this data looks like. I'll start with the radio. So what we've done is we've selected the complete sample of all the double-peaked AGN in Sloan that are redshifts less than 0.1, so the closest ones. And there's 71 of these. And so our plan is to get the Longslit observations and the VLA radio observations for all 71 and identify what is producing the double peaks in all 71 and which ones are dual AGN versus outflows versus disk rotation. So we've gotten the data in for the first 16 of these objects, and this is work that my postdoc Francisco Mueller-Sanchez has done. And he found that of the 16, 3 of them are dual AGN. And we can tell that because we see 2 radio cores in the radio data. These are flat spectrum radio cores, and they correspond to where the 2 emission peaks are that we saw in the Longslit spectra. And this red dashed line shows the orientation of the major axis of the host galaxy. So the host galaxy would be going like this. So the 2 AGN are orbiting in the plane of the host galaxy. And then the yellow shows the orientation of the 2 oxygen-3 emission components we saw in the long-slit spectra. So the 2 radio components orient with the same orientation and separation as the oxygen-3 as well.
So why this cannot be outflow?
So these cannot be outflow because these are 2 well-defined, spatially distinct radio sources that have flat spectra. This is showing the spectral index map for the data. If it was a radio jet-driven outflow, then you would see extended radio emission with a steep spectrum. And I'll show you one of those in a couple of slides. So what you need for confirmation of dual AGN are compact, well-separated flat spectrum radio cores. And these also correspond, we see oxygen-3 emission that lines up with both of them. So there were 3 cases where we saw this. And so the separations we measured were around a kiloparsec for each of them. Now, if you're anything like me, you want to know what these galaxies look like. This is dual AGN. This is a merger. What does a host galaxy look like? Does it look like a merger? Well, these are the Sloan images of these galaxies. So these are low-resolution, ground-based images. So this one, it doesn't look like much. It just looks like an edge on this galaxy. Doesn't really look like a merger. But there are the 2 AGN in the plane of the disk there. This one, by itself, it doesn't look like much, but it looks like it has a companion with a tidal tail that's maybe interacting with it. So maybe it recently had an interaction with this galaxy, or maybe it's coming in for a merger. But this galaxy itself doesn't look like much. And this one, similarly, I don't see any signs of a merger in this one. So this underscores the point I made at the beginning, that it is difficult to identify galaxy mergers just from their morphologies. We know that all of these 3 are galaxy mergers because they have 2 AGN in them. How else are you going to get 2 supermassive black holes in a galaxy if not through a merger? But when you look at the images, you wouldn't necessarily pick these things out as mergers. So that's why there's been this observational discrepancy when you try to link AGN to mergers. So this is a new way of coming at it. Now, what I would really love to get is high-resolution images of these galaxies. So, for example, with the Hubble Space Telescope or with adaptive optics-aided imaging. Then you might be able to see, tidal features or other, small resolution features that you can't see from the Sloan images alone. So I'm curious what they look like in high resolution. If they still look like they're isolated and not merging, or if merger signatures come out, if you stare long enough and at high enough resolution. Okay, so 3 dual AGN. What about the rest? So 5 of them turned out to be outflows, AGN outflows, that are being driven by radio jets. And the way we know that is that we see 1 radio core and then extended radio emission that has a steep spectrum to it. So this is the AGN here, and then it's got jets going like this. And you can see that it's not lined up with the major axis of the galaxy anymore. So this would be a jet, an outflow that's coming out of the plane of the galaxy. So 5 of them look like this, and then the rest of them are just single radio cores with no extended structure at all. So for those, the radio doesn't help you that much. So you have to turn to the Longslit spectra to see what's going on. And so you can look at the Longslit spectra. If you see extended oxygen-3 emission, then that's an outflow that's just driven by something other than a radio jet, so mechanically or radiatively driven AGN outflow. Or if you see in the Longslit spectrum a velocity profile that's Keplerian, then you know that that's disk rotation. So you're just seeing rotating disk around a single AGN. And so at the end of the day, we found that, so these are the ones I showed you, so 20% dual AGN, 30% radio jet-driven outflows. These are the ones where we see a single radio core with no radio jet, but in the long slit data, we still see evidence for an outflow, so it's a radiatively or mechanically driven AGN outflow, and then 10% rotating disk with Keplerian profiles. So this is the results from the first 18. So we'll be able to improve the precision of this once we get the full sample of 71. But you're seeing that about 70% of these double-peaked profiles are actually produced by outflows. The dual AGN are only 20%. So if you remember, you start out with all supermassive black holes. 5% of them are AGN. 1% of them are double-peaked. And then 20% of those are actually dual AGN. So you see why I have to have a really large sample to start with to do anything with this. Okay. All right. So that's the VLA data. And so we've got observations coming in for the rest of the 71 to fill out this sample. And then what we want to do is team up with a theorist to get some sense of what these data mean in the broader context. And so Laura Blecka does simulations of merging galaxies where she could follow when the black holes turn on and off as AGN and what their velocities and separations are as they merge. And so what she can do is take her simulations and then create mock-up of spectra of what her merging galaxy, simulated galaxy, would look like if you observed it with our telescopes. So here's an example of, she's got a single AGN with a rotating disk, and it's producing this mocked-up double-peaked profile. And this is what the 2D spectrum would look like. And here's an example of a merger with 2 AGN producing a double-peaked profile in its long-slit spectra. So what we can do is we can take all of our observations of the disk rotation, dual AGN, and what they look like in our spectra and compare them to the mock-up spectra from the simulations. And what this does is it helps us understand the selection effects in our method. So we're selecting things that have double peaks. So we're selecting only for the dual AGN that have velocities that are large along the line of sight. Now imagine you had dual AGN, but their velocities were mostly in the plane of the sky. It wouldn't produce a double peak profile. We wouldn't pick it up in our selection technique. So by comparing to the simulations, we're able to figure out how many of those were missing because of our double peak selection criteria. Now you notice I showed examples from the simulations of what disk rotation, double peaks from disk rotation dual AGN look like, but I don't have one showing the third option, which is outflows. And that's because it's really hard to numerically model AGN outflows. So the theorists are helping us out by helping us understand our selection biases. We can also help them out because we've got this giant sample now with this beautiful optical long slit and radio data for all of them. We figured out which ones are radio jet-driven outflows, which ones are other outflows. So we can give all this data to the simulators. And so Laura's going to use the data to build better numerical models of what AGN outflows look like from a simulation standpoint. And the last thing that we're going to do with the simulations is try to get out these black hole merger timescales that I talked about are important for gravitational waves. So this is a plot from Laura's simulations showing the time until merging for the two black holes, until the two black holes coalesce, against the separation of the black holes in the merger. And these 3 dashed lines show the separations of the 3 dual AGN that we've found so far with this radio data. And so you can see for any given dual AGN that we found observationally, you can see there's a range of time scales for the black holes to merge. So something from 10 to 300 million years from this plot. And this is just showing the projected black hole separations. We also know their line of sight velocities, their luminosities. So we can use those other parameters to really beat this down and get even tighter constraints on what the inspiral timescales are. So that's another thing we're going to do once we have this big sample. Okay. Now the X-ray data. So I said we can confirm dual AGN with either radio data or X-ray data. And so we've gotten Chandra and Hubble observations for 10 of these double-peaked AGN. And we found that 6 of them are actually galaxy mergers because you can see there are 2 stellar bulges in the galaxy. So that means those are the 2 remnants of the merging galaxies. And so let's see, 4 of these are major mergers, which means that the 2 stellar bulges have comparable masses. So 2 galaxies that are merging of comparably large size. And 2 of them, this one and this one, are minor mergers, where one galaxy is much less massive than the other. So this is telling you something about how you form these dual AGN. Are they in minor mergers or major mergers? Turns out it looks like it's a bit of a mix, which was a surprise because people thought it would just be major mergers. So 2 big galaxies bringing lots of gas to fuel both black holes. Now, so we can measure the X-ray luminosities of the AGN and compare to the oxygen-3 luminosities that we know from the optical data. And we found that for the AGN that are in mergers, their X-ray luminosities are much lower for a fixed O3 luminosity than single AGN that aren't in mergers. Okay, so AGN and mergers have lower X-ray luminosities than you would expect for a comparable AGN that's not in a merger. So what we think is going on here is that the merger itself is powering these gas inflows towards the center of the galaxy, and then that gas is absorbing the X-ray flux from the AGN. So the X-ray flux is produced from the accretion disk region very close into the black hole, whereas the O3 flux comes from larger scales of the narrow line region. So gas in the center of the galaxy merger would preferentially absorb the flux in the X-rays and not as much the O3 flux, oxygen 3 flux. So that's why we think the AGN and mergers have lower X-ray luminosities. But this was a surprise. So when we were planning the Chandra observations and we had to say how long we needed to make these exposures to get the number of counts we needed to identify an AGN, all we had was the oxygen 3 luminosity. And so we used the oxygen 3 to X-ray luminosity scaling relation for single AGN, which is all there was at the time. And so you see, using that, we ended up predicting exposure times that were much lower than what we actually needed to get the number of photons for a firm AGN detection. So the result of that is we need more telescope time to know for sure. So for right now, I'm not gonna say which of these I think have 2 AGN versus only 1 AGN, because the data analysis is very touchy because we don't have many photons. And so I'm still figuring out which ones I really believe. But with more data, I'll have more certainty. Yes?
The low X-ray luminosity, that's like more like a selection effect, some orientation. So when you select this oxygen, based on the oxygen line, you're more likely to select the system. The rotation is more like an edge on.
Yeah.
So they have higher like a column for X-ray.
Yeah, so that could be another effect. So for us to get large line of sight velocities to produce the double peaks, it has to be an edge-on, or more likely to be an edge-on galaxy. So you're looking through a bigger column of the galaxy too. So that could be another effect that's causing the X-ray luminosity to be lower than for AGN that aren't in mergers. Yeah, just the fact that we're selecting for these double peak lines. Yeah. Yep.
Was the selection? It seems like you have a better success rate for the Chandra observations than for the VLA observations.
Mm-hmm.
Why is that? What did you do that made that sample more successful?
Yeah. So I'll tell you. Okay, so the Chandra data, using Chandra is more limiting because Chandra doesn't have as good of a spatial resolution as the VLA radio. So Chandra can do, it can resolve 2 X-ray sources with separations of about half an arc second. Whereas with the VLA, it can do 0.2 arc seconds. So when we were selecting Chandra targets, we chose the ones where the Longslit data showed separations in the emission components of at least half an arc second. So that's one selection effect. These ones are larger separations. The other thing is, so you don't want to ask for a prohibitively large amount of Chandra telescope time for any observation that you want to do. And so to minimize the Chandra time that we needed, we selected the galaxies with the highest O3 luminosities for Chandra, because then you need the shorter exposure time to get the X-ray luminosities that you need. And so I think that this is a selection effect mostly of that. We're selecting the brightest AGN. Remember, the theory predicted the brightest AGN should be the ones that are in galaxy mergers. Whereas with the VLA data, we didn't have that limitation with the luminosities, or so much with the spatial separation. So the VLA data, we just did it all. We did everything, all the galaxies, redshift less than 0.1. Whereas with Chandra, we had to be picky to get the ones that we could observe without taking up too much telescope time. Okay. So, and this is coming back to this idea. So the theory predicted that mergers should preferentially trigger the most luminous AGN and not the less luminous AGN. And so we were able to test this with this small sample of 10 galaxies that we observed with Chandra. And so we found that the 6 AGN that are in mergers are an order of magnitude more luminous than the 4 that aren't in mergers. So this is a small sample, but this is the first line of, I'd say, direct observational evidence supporting this idea that the more luminous AGN are the ones that are induced by mergers. Okay, so the whole point of this thing was, I told you I wanted to build up a large catalog of dual AGN so I could learn something about galaxy evolution. We started with 4. I showed you this whole 3-step technique, all this trouble we're going through. So how are we doing? Okay, so this is about 5 years ago when we started actually looking for these things for real. And this is work done not just by us, but by several other groups that have been working on these double-peaked AGN, looking for dual AGN. And so, it took a couple years for the first bits of data to come in. We found a couple. Then the first X-ray data started coming in. Then the radio data started coming in. And so we're to the point now where there are 16 known dual AGN. We went from 4 to 16. And we've got all this extra radio and long-slit data coming in. And so if that success rate, remember with the first 16 we found that 20% of them are dual AGN. So if that holds true with the rest of the data that's coming in, then by next year we could be up here around 26. So look at this, exponential growth. It's going to be literally through the roof here. So that's how the search has been progressing so far. We're finally building up, getting towards a statistically significant sample to start to get at these questions in galaxy evolution. So I'll summarize with the 3 steps to finding dual AGN. Select candidates from large spectroscopic surveys of galaxies, the objects with double peaks. Get some follow-up long-slit data, some X-ray and radio data, and this is what you really need for the confirmations. But these steps help you find the best candidates to go after in the radio and X-ray. And the first results that we've been getting so far from we've got 16 dual AGN now, is we are finding first tentative evidence that the higher luminosity AGN are the ones that are preferentially triggered by gas inflows during galaxy mergers. We found a couple of dual AGN that are in minor galaxy mergers, small galaxy merging with a big one. Most are still in major, but we have to explain these minor merger ones and how the gas gets onto both black holes. And the part I'm really excited about is finally lining up all these observations with the theoretical context and the simulations. And this will really help us not only understand our selection biases, but also start to get at these tight observational measurements I promised you for the black hole merger rate that we can use for gravitational wave experiments in the future. Thank you. Yep.
Are any of these 16 gamma ray emitters?
Not that I know of. I don't think they've even been observed in the gamma rays. So people have been pretty much going radio through X-ray. That's been the extent of the electromagnetic spectrum for most of these observations. Yeah.
So you mentioned there's other people kind of doing this as well.
Mhm.
Are they all employing the same kind of 3-step method, or do they have other aims?
They have, so people have different approaches. I showed some of the near-infrared. I showed one of the near-infrared images. And so there are a couple groups. So that's something that my group is not doing. But there are groups that are working really hard to get high-resolution near-infrared images where, of the double-peaked AGN, looking for the ones with the 2 stellar cores. Because if you have 2 stellar cores, you're probably a galaxy merger, so that's a really good candidate for dual AGN. So that's a good angle to go to. And then some people start with the radio. So they start with large surveys of the radio sky and then look for things that look like they're 2 radio sources. But then it could be, a radio jet or something. So then they go get long slit or optical spectroscopy. So you can kind of do these things in different orders. Yeah.
In the Sloan data that you were looking through to look for the double peaks, did you have a lot that where the oxygen 3 and the H beta lines overlap?
Well, the oxygen and the H beta are very well separated in wavelength, so they don't overlap. But as the double peaks, as the line of sight velocity separation gets smaller, then the space between the double peaks will get smaller. So at a certain point, we can't even tell that it's double peaked anymore, and we wouldn't pick those guys out. But the H beta is around 4861 angstroms, and O3 is all the way over at 5007.
Because I was looking at, like last year I was looking at, well, I was helping someone do like Redshift calibration for
Mhm.
Sloan, and we were modeling like the O3 lines, and we had a bunch that like where the oxygen 3 line was merged. I can't remember what line it was now.
You might be thinking of H alpha and nitrogen 2. Those are very close lines that can be blended.
There's also 2 oxygen 3 lines next to each other.
Right.
So when you're modeling the peak, you have 2 peaks. You just model them as 2 Gaussians,
Yes.
right? Okay, and you do that across all of the galaxies.
Yes, so you take all the galaxy spectra where you've identified there's an AGN there, and you can do that by measuring the fluxes of the line. So you take the sample of AGN spectra, and then you just fit Gaussians, and you have to have some threshold for what counts as 2 Gaussians fit this one a lot better than 1 Gaussian. Yeah.
Yeah. Well, but then you could stack, right? You stack it from most separation to least separation. At some point, you're still getting galaxies that have separation, but you're not quite resolving them.
Yeah, and so that has to do with the spectral resolution of the data that was taken with Sloan. And so we can't do better than about 100 kilometers a second. That's the smallest velocity separation that we can actually spectrally resolve.
But would it be possible to play to do any like experiments right at that line of where you're not seeing anymore? Trying to push that boundary just basically by having a stack of.
What you could do is look for a lumpy single Gaussian profile that's not quite single and it's kind of lumpy. Yeah, you could take that to try to push it to smaller velocity separations. Nobody's done that yet, though. Yep.
So the fact that you're finding most of them at 1 kiloparsec, do you think that's a physical effect or a selection effect?
I think it's both. So first of all, these are Sloan selected. So everything that's happening is in a 3 arcsecond fiber. So you have to have double peaks within a 3 arcsecond fiber, which is about, at this redshift range, within about 5 kiloparsecs.
Okay.
But it's kind of interesting that everything isn't at 4 kiloparsecs or, 0.1 kiloparsecs.
You generally expect more and more as you go to larger radii, right? Because there's more volume there.
Yeah, but it also has to do with at what point is the black hole getting the gas.
Right.
So it might be spending more time in the AGN phase at smaller separations while the gas is at the center. So that's one of the things that comparing with the simulations will help, because we've got the selection effects of we don't know the 3D separations and velocities. So the simulations will predict, they actually do predict that the closer 2 black holes get together, the more likely they'll be to both be AGN. And so with the observations, we can actually test that once we get enough of these. Yeah.
And for the it seems to me like a very sketchy to have this black hole in spiral timescale based on this only 20 observations. You need a large number of continuous. Also,
Yep.
it also depends on where, again, where the black hole gets gathered, right? So it seems that, and also depends on the black hole mass, the whole galaxy, stellar mass, all this. Seems pretty sketchy there.
Yeah. So the more parameters you can add, so we can measure the host galaxy stellar mass. We can do more observations to get black hole masses. That just offers more constraints on that wide range of inspiral timescales that I showed. And also, the more objects we get, the better we can constrain this down. But this is the closest to black holes merging that we can get observationally. So this is our best observational hope for doing this.
It's still dominated by the dynamic friction timescale.
Yes.
Right? So it's not
Yes. No. This doesn't take the black holes down to the gravitational GR regime. No. These are larger scale hydrodynamic simulations where it's dynamical friction that's drawing them together. Yeah.
And are you thinking about doing actual dynamical friction simulations? Because I know it kind of depends on things that are like not like on the dark matter halo phase density phase density distribution. And stuff
Yeah.
like that. Are you doing that kind of thing, or
I've done.
is Laura doing that sort of thing?
So I've done just the analytical calculations for
Yeah.
dynamical friction to get timescales, but that's an oversimplification.
Yeah.
So you can really do more with the simulations because you can have different gas fractions in the galaxies, different orbital parameters as they merge. So I think that's the best way forward is to look at the range and parameter space from simulations.
All right, great. Let's thank.
I was sitting there thinking.
Hi, my name's Ines. I'm going to be meeting with you more after this. Okay, great. For now, I just want to say I really enjoyed it.
Oh, thank you. Thank you so much. I look forward to seeing you tomorrow.
So I asked you about. So I mean, I guess if you're looking at the doublet, then it doesn't really matter. But if you're modeling the actual.
What you have is mine are all airline type 2 AGN. You have a type 1 AGN.
Okay. Luckily, so you're also back on it. So okay, there's one more thing.
Yeah. I don't have your problem.
Yeah. Well, I don't have it anymore.
I got 9 problems, but yours isn't one.
His problem now is Osiris. Yeah.
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 Ooh, I'll show some Osiris data tomorrow.
Okay. Let's see. Just a second, I'll be right back.
Sure.
So what, what would be a good time for you for our dinner?
For dinner?
Yeah.
Anil said 6, but I can go anytime. I don't have anything to do, right? So.
Yeah, okay, so let's plan like 6, around 6 or 45.
Okay.
Maybe around 5:45.
I'm staying in Adam Bolton's office.
And the person, okay,
Yeah.
okay.
Okay.
Okay, so I know.
Okay.
Okay, so yes, my office is just next to Anil.
Oh, okay. So we'll just yell down the hallway.
Yeah, okay.
Okay, sounds good.
Sorry, I didn't mean to. I was just trying to muscle my grad student. She's a first year student, and I was trying to get her to take me lunch.
Yeah.
She's a,
Yeah. Yeah. That's
so she's gonna do it, but she's like, I have no any restaurants.
I know a burrito place, so we'll be fine.
Yeah, it's cool. I didn't it's interesting that I guess I'm a little surprised that there's actually. I would have expected the distribution the other way. You know, that you'd have more at 5 kiloparsecs than 1 kiloparsec. So I mean, it has to be a pretty dramatic. Right? It's just the time spent must be larger and larger radii.
Yeah.
So it must be a pretty
I think
dramatic
it's
difference in the gas availability.
It's the AGN fraction. So, you know Sarah Ellison's work on okay, so she's looked at Sloan galaxies and which ones have AGN as a function of separation from 100 kiloparsecs down to like 10, and you can see this increase. AGN fraction goes up as things get closer. And then it hasn't really been well studied at less than 10 kiloparsecs. But the simulations say that the march should continue, and then peak AGN fraction should peak around, like half a kiloparsec or something.
One of the interesting things with the UCBs is that they have to pass within about a kiloparsec of the center to, fully stroked. So that's also kind of a magical number for I mean, roughly speaking.
Yeah.
So that would be a.
Maybe it's related physically.
Yeah, I mean, well, I guess what I'm saying is that just because you see two objects at 1 kiloparsec separation that are AGN doesn't necessarily mean they're going to merge either.
Right.
Right, because they can, if you have a very elongated orbit, then they can the dynamical friction timescales.
Right, and that's one thing that came out of the simulations, and is the reason that there's such a large range in the inspiral timescales. Is that sometimes you catch it on first pericenter passing, and so it takes a long time to finally get there.
Yeah.
And so Laura and I have been talking about ways to tell whether you're at pericenter or whether you're actually in for the comet thing.
Yeah.
Ways we can kind of sort out between the two. And one of the things she noticed was